Okay, this is going to be our last video on benzene substituents. In 118b, we covered several reactions adding different substituents to benzene rings, and you will need to use some of those in your syntheses with this chapter as well. So take a minute and try and think about what reagents should go across each of these arrows. Okay, so these should all look pretty familiar. Remember that our sulfate group can end up being removed with acid and water. So your nitro group can be reduced to an amine. That's going to be important for the later part of this video. And the rest of those are our Friedel-Crafts, the Clemmensen reduction, and then as well as remember that that has a benzylic hydrogen, so that reaction is also from our carboxylic acids chapter. A couple more reactions we're going to talk about with phenols. We can turn those into enolate ions. So if we have carbon dioxide, we can make that into a nice new carbon-carbon bond on the ortho position relative to our phenol. A more common reaction is going to involve an ether. It's going to be called the Claisen rearrangement. We're going to go from an unsaturated ether to two groups, a phenol and a chain of unsaturation on the ortho position. This is going to be a concerted mechanism. 3 arrows very easily. We're going to move a 6 electrons, so it's going to remind you of an aromatic system. Something to look for here is going from an ether, being able to predict this product, having it move over one position. So your mechanism is actually going to involve your benzene ring acting as a nucleophile, so your enolate ion pushing down. We can then have our carbonyl regain aromaticity, giving us our phenol with our carbon chain rather than being attached to the oxygen, attached to the ring. We also see this in allopathic systems where we don't have a ring attached, but our incentive here would, rather than have that CO bond in the middle of our ether, we can take that into a aldehyde. Remember in the last set we had our phenol being gained because of aromaticity. Here we don't have that, so our keto-enol tautomerism is going to remain at an aldehyde, not an alcohol. You also can use this with just carbon systems. Here, looking at where our double bonds are in the terminal position, we can draw the same 3 arrows, giving us a multi or more substituted double bond relative to our starting product. The last thing we're going to talk about is diazotation. It's going to turn an amine group into that azo group. That azo group is nitrogen gas, easily going to be able to leave. So whatever nucleophile is around is going to add at that position. So if we have water around, we can have that azo group leave, then turn that into a positively charged position on our benzene ring and give us our alcohol. The other reaction that we also use in conjunction with this is a series called the Sandmeyer reactions. So they're involved cupric salts. These look very similar to reagents as far as what we talked about in the review, things you've seen in chapter 16. So a copper chloride would add a chlorine in that position. Copper bromide, same thing. New one is that we now know a way to add a nitrile group onto a ring, which is nice because we do know all that chemistry we covered in the carboxylic acid chapter. We can turn that back into an amine, we can turn that into a carbon chain, we can turn that into an aldehyde, lots of different synthetic routes. Another one is we can also turn that amine into our azo group and have the azo group leave, and with this new reagent hypophosphorous acid, it's just a very non-nucleophilic source of hydrogen, so we can completely remove that. Notice here having a methyl group and a bromine, depending on where you start, having those in a meta relationship could be pretty difficult. So we have the advantage of using our amine group as a director with EAS. So if we wanted to get from a benzene ring to a meta-substituted bromine, it'd be very difficult to use with our old methods. We need to use we could use nitro group, added 2 nitro groups. If it's an excess, we can reduce those down to amines and then add our bromines. If we did not use this method, we would only add the second bromine probably in the para position due to steric effects. This is another reaction map filling in reagents for the rest of the series. These could be some other intermediates in a synthesis. Pause the video and try to fill in these arrows. Okay, the first one you'll notice I started with NH2 on here, so we know how to add that, or at least how to get that from a nitro group. We can turn that into our azo compound and then use any one of these series to add any one of these specific substituents. That's it for benzene substituents video.